A meteorite big enough to sink a coastal city into the ocean would not create a whirlpool. It would create something far worse and far stranger, and the whirlpool part is where the science quietly falls apart. Here is the mystery. Almost every disaster movie imagines an ocean impact the same way, a spinning vortex opening like a drain, dragging ships and shorelines down into a swirling throat of water. It is a great image. It is also physically backwards. Water does not behave like a bathtub when something the size of a mountain slams into it at cosmic speed. To understand what actually happens, we need to follow the energy, because that energy has to go somewhere, and where it goes is the whole story. Start with the impact itself. A meteorite large enough to matter, say a few hundred meters to a kilometer across, would be moving at somewhere between 15 and 30 kilometers per second. That is over 50 times the speed of sound. At that velocity, the object does not simply splash into the ocean, it detonates. The kinetic energy converts almost instantly into heat and shock, vaporizing the meteorite and a huge column of seawater in a fraction of a second. We have real-world proxies for this. The asteroid that ended the Cretaceous period, about 66 million years ago, struck what is now Mexico's Yucatan Peninsula, and even though that was a land impact, it released energy estimated at over 1 billion times the Hiroshima bomb. An ocean strike of a similar or even smaller scale would behave in some ways more violently, because water transmits shock differently than rock. So instead of a whirlpool, the first thing you would see is a cavity. The impact blasts a temporary hole in the ocean, sometimes kilometers deep, as water is violently pushed outward and downward. This is called a transient crater, and it can briefly expose the seafloor in shallower waters. But water does not like empty space. Gravity and pressure immediately start rushing back in to fill that void, and this is the moment the real killer is born, not a spinning vortex, but a tsunami. Here is the mechanism, step by step. As the cavity collapses, walls of water rush inward and upward from every direction, colliding at the center and throwing up a towering central peak, sometimes referred to as a central jet, that can rise higher than the original ocean depth. This collapsing and rebounding motion radiates outward as a set of enormous waves. Unlike a whirlpool, which would need a persistent rotational sink pulling water downward in a stable circular pattern, an impact site simply cannot sustain that. The energy released is too explosive and too brief, more like a bomb going off underwater than a drain slowly opening. Ocean tsunamis generated by real events, like the 2011 Tohoku earthquake off Japan, moved at speeds up to 800 kilometers per hour in open water and still devastated coastlines with waves over 10 meters high. And that event released only a tiny fraction of the energy a serious meteorite impact would unleash. Now scale that up. Simulations run by researchers, including work from Los Alamos National Laboratory and Sandia National Laboratories using models of asteroid ocean impacts, suggest that a meteorite 1 kilometer wide striking mid-ocean could generate initial waves near the impact site over 100 meters tall. As these waves travel across open water, they lose height, spreading their energy over greater distances, similar to ripples widening as they move away from a stone dropped in a pond. Depending on the depth of the ocean and the distance to shore, waves reaching coastlines might be reduced to something in the range of 10 to 20 meters, still catastrophic. But importantly, this is a wave train, a series of surges arriving over minutes to hours, not a single collapsing vortex swallowing ships whole. This is where the ship-sinking whirlpool idea really breaks down. Ships are actually more vulnerable to the initial blast wave and the airborne shock front than to any imagined suction. The impact would also throw an enormous plume of vaporized rock and water high into the atmosphere, and this plume matters just as much as the wave. Depending on the size of the impactor, debris injected into the stratosphere could block sunlight for months, similar to the global cooling effects proposed after the Chicxulub impact, which some studies suggest dropped average global temperatures by several degrees for years afterward, contributing to mass extinction on land and in the sea. So the true chain of destruction looks like this. First, a flash of light and heat capable of igniting fires and causing burns hundreds of kilometers away for larger impactors. Second, a shockwave through the air, moving faster than sound, capable of flattening structures across a wide radius. Third, the tsunami, arriving in successive waves, the true city killer, capable of pushing seawater kilometers inland depending on coastal topography. Fourth, longer-term climate disruption, as ejected debris and sulfur aerosols spread globally, potentially triggering years of reduced sunlight, crop failures, and ecological collapse. It is worth remembering scale changes everything here. A small meteorite, say 20 meters across like the Chelyabinsk object that exploded over Russia in 2013, would burn up or detonate in the atmosphere with far less consequence, releasing energy equivalent to around 500 kilotons of TNT, powerful, but nowhere near ocean-altering. It takes an object several hundred meters wide or larger to generate a truly civilization-threatening ocean event, and thankfully, asteroid tracking programs like NASA's Center for Near-Earth Object Studies currently know of no such object on a collision course with Earth in the foreseeable future. Objects that large are also rare, statistically expected only once every several 100,000 to few million years based on crater records and orbital surveys. So the whirlpool was never really the danger. The danger was always the wave, invisible in its buildup, arriving with the patience of physics rather than the theater of cinema. It reminds us that Earth's oceans are not just scenery, they are an enormous reservoir of stored energy, ready to transmit whatever violence strikes them across entire coastlines in a matter of hours. Which leaves an open question worth sitting with. If the ocean can turn a single point of impact into a planetary-scale event, how much of Earth's history, the extinctions we know and the ones we have not yet found evidence for, might be written not in the craters we can see, but in the waves that came after and vanished long before anyone was left to measure them?